Okay. So in this video, we'll be looking at, we'll still be looking at amino acids, but we'll be combining different amino acids to form molecules called peptides. That we know from previous chapters that carboxylic acids plus amines can create amides. And amino acids have both carboxylic acid and amines in their molecules. And so, of course, like any other carboxylic acid or amine, we can form an amide using amino acids. And so if we'll just use alanine and glycine, and we combine this carboxylic acid of alanine with this amine of glycine, then we can produce this amide. Where what we have here we've been calling in amide functional group up to this point, but when we're discussing amino acids and these amide bonds, we also call this a peptide bond. And so it's just another name for the same thing, that this carbon-nitrogen bond here is referred to as a peptide bond when it exists between two amino acids. And not to confuse things, but we also call a chain of amino acids a peptide. And so because this peptide here is made up of two amino acids, alanine and glycine, it is a dipeptide. So this whole thing is a dipeptide, whereas this bond right here in the middle is the peptide bond, which is also an amide bond. And so, like if we have this dipeptide made up of two amino acids, we can have tripeptides made up of 3, tetrapeptides made up of 4, pentapeptides made up of 5, and so on and so forth. That when we classify this, we'll say that amino acids combine to form peptides. And an oligopeptide, similar to an oligosaccharide, contains anywhere from 2 to 10 amino acids. And a polypeptide contains 10 or more amino acids. And now the book says that what we call proteins begins at about 50 amino acids. But in my experience, 50 amino acids would be a very small protein. Not impossibly small, but pretty small. And the difference between a polypeptide and a protein is kind of arbitrary because I've worked with polymers made up of polypeptides that are 70 amino acids long, but all 70 of those amino acids were lysine. And so it was a polypeptide made up of a single amino acid copied over and over and over and over and over again. And so by this 50 definition, that polylysine would be a protein. But I've never heard of it referred to as a protein. It's always been referred to as a polypeptide, even though it has 70 amino acids instead of 50. Anyway, the exact definitions don't matter too much, and that we know that oligopeptides are your shorter peptide chains. Your polypeptides are your longer peptide chains, and at some point it switches over from polypeptide to protein. So while we're discussing peptides, we'll draw out a pentapeptide. Okay, so this is a peptide made up of 5 amino acids. We have 1, 2, 3, and 4 peptide bonds. And we'll go ahead and label the amino acids. We start with alanine, then we have glycine, then we have serine, valine, and another glycine. You'll notice that we start here on the left side with the amino end, and that's customary when drawing peptides. We always start on the amino end and we stop at the carboxylic acid end. And we have special names for these two ends. The amino side is called the N terminus, and the carboxylic acid side is called the C terminus. And so we know that these peptide chains can be much longer. We've discussed how this would be an oligopeptide at just 5 amino acids. But if we had more than 10 amino acids, we could call it a polypeptide. If we had more than 50 amino acids, we could call it a protein. But a 50 amino acid protein is very small. Most proteins have hundreds of amino acids. There is one protein in particular, the largest protein ever found so far, called titin, T-I-T-I-N. And this is a muscle protein. And some forms of titin have around 35,000 amino acids. And so that makes it by far the largest known protein in nature. And it's not just the largest known protein in nature. If we were to write out the official name for the titin protein, if we went like alanine, glycine, serine, valine, glycine, and we named all the amino acids, it would also be the longest word in any known language at almost 190,000 letters. That it would take over an hour to name all the amino acids in titin. So it's a humongous molecule. But anyway, moving on to some more properties of the peptide bond. That peptide bonds, like all amide bonds, can be hydrolyzed. That they can be combined with water molecules and cut. And so if we were to take, let's say this bond here, and we were to cut the molecule here through hydrolysis, then we would wind up with 2 peptides instead of 1 peptide. We'd get this first segment, plus this second segment. And so the hydrolysis reaction can take this one pentapeptide, and we can cut it here, and we can get this tripeptide and this dipeptide. Let me go ahead and label those peptide bonds again so it's a little more clear. That we have 3 amino acids on the left and 2 amino acids on the right. That this is an important reaction when digesting proteins. So if you eat, protein-rich food like meat or beans, then your digestive system has to cut these peptide bonds to make those proteins small enough to absorb. And so we have enzymes that are designed to catalyze this hydrolysis reaction and cut up the peptide chains into smaller peptide chains. Now, we should also discuss how peptides respond to changes in pH. That because they're made up of amino acids, and amino acids respond to changes in pH, peptides can also respond to changes in pH. And so let's look at 2 tripeptides, so there will be 3 amino acids each, and how they respond to changes in pH. And the first one that we'll look at is lysine, serine, aspartic acid. So we'll begin at pH equals 1. So a low pH, a highly acidic solution. We'll draw lysine. Then serine. And then aspartic acid. And I'll try to color code this. And so at a pH of 1, we have 2 different amine groups that can be protonated, the N-terminal amine group and this amine on our lysine side chain. We also have 2 carboxylic acid groups that can be protonated, the C-terminal carboxylic acid plus the side chain carboxylic acid on our aspartic acid. So at pH 1, everything will be protonated And so our two amino groups will have positive charges, and our two carboxylic acid groups will be neutral. And so our overall charge is 2 plus. So let's change the pH now. Let's go from a pH of 1 to a pH of 7. So now things are neutral. At pH of 7, our amino groups are still positively charged. They're still protonated, but our carboxylic acids will lose their protons and they'll become deprotonated. It'll become negatively charged. So now we have two positive charges, two negative charges. Our overall charge now is 0. And if we change the pH again, we'll go from 7 to 14. Then not only will we pull the protons off of the carboxylic acids, we'll pull a proton off of each amino group. And so we'll go from NH3 to NH2, and we'll lose those positive charges. And because we lose these positive charges, but we still have these negative charges, the overall charge becomes 2 minus. And so we can see how the charge of the molecule changes as the pH of the molecule, or the pH of the solution changes. So we'll look at one more tripeptide. This time we'll look at lysine, alanine. And so we'll draw out the molecule at a pH of 1. And so at a pH of 1, now we have 3 amino groups that can be protonated because we have the N-terminal amino group plus 2 lysines that each have an amino group on their side chains. And so our 3 amino groups will all be positively charged. Our C-terminal carboxylic acid group will be neutral, and so our overall charge becomes 3 plus. If we change the pH to 7, then these 3 amino groups will still be positively charged, but our C-terminal carboxylic acid group will lose a hydrogen atom and become negatively charged. And so our overall charge drops from 3 plus to 2 plus, because this negative charge will cancel out one of our 3 positive charges. And if we change the pH again, from 7 to 14, then we lose a proton on each of these amino groups. So we lose that positive charge on each amino group. They go from NH3 to NH2. And our charge now goes from 2 plus to 1 minus, because this carboxylic acid is still negatively charged. And the charge, the changing the pH changes the overall charge of these molecules, but that has more effects than just changing the charge. It also changes the solubility. The charged molecules tend to be more water soluble than non-charged molecules. And so if we were to adjust the pH just so to get a zero overall charge, then it would become much less water soluble than if we have high pH or low pH, where we have more charges on the peptide. So controlling the pH also controls the solubility of the peptide molecule. So that's our introduction to peptides, and we'll get more into larger peptides and proteins in the next video.